Hello friends, this video is about how to make a text terminal on an STM32. The idea for the video wasn't just a random one. I'm currently working on something similar and decided to implement the firmware using FreeRTOS. While writing a program using FreeRTOS, I ran into a problem. I completely didn't understand how much memory to allocate to a task. And with this random memory allocation approach, I couldn't allocate the necessary RAM for the task. The STM simply ran out of memory. As it turns out, FreeRTOS has built-in function for diagnosing tasks and identifying unused memory in a task. I found some great articles here on how to display unused memory allocated to a task in the console using the command interface, but this terminal or command interface still needs to be configured. I'll cover that in this video. In this video, we'll set up a project in CubeMX. We'll set up and connect the text terminal. We'll add the necessary command. We'll run tests and display useful information. I made this video based on information from the HALT articles. Thanks to the author of those articles, I learned a lot from them. I'll leave links to useful information in the description, but I made some minor modification to work with ST-HAL. I also used FreeRTOS in the video. I recently started learning this system myself. For further study, I recommend Vladimir Medintsev's video. I'll leave a link in the description, as well as his books on FreeRTOS. Understanding these topics will be sufficient for understanding the information in today's video.
Let's create a project in CubeMX. I am using an STM32F103C8T6 on my Cheburlyator debug board. So we'll name the project that. First, we need to configure the GPIO. It needs to be configured to match the pins on the Cheburlyator debug board. We'll control this TB6612 chip from the terminal. We will write a monitor control task that will use data from the terminal to control the motor's acceleration and rotation direction. We have configured the pins. Now let's assign them symbolic names. Pair 5 is used for power management. Here's how it looks in the diagram. All my power supplies are enabled by this pin, except for one that powers the microcontroller. I keep this one always on U5. It supplies power through a regulator U7 to the microcontroller. The others are enabled by the P-enable pin when a high voltage is applied here. Q2 opens and enables all the power supply circuits. I'd like to point out that the output of the 12-volt setup converters, when the circuits are disabled, will show the battery supply voltage. One of the power supply microcircuits power the monitor control microcircuit. We will be using motors rated for 12 volts. Next, we will assign symbolic names to the pins responsible for rotation, direction and PWM resolution on the TB6612 microcircuit. All possible modes can be found in the microcircuits documentation. Let's open it and look at the table. It defines the levels of each microcircuit's control input and matches them to the output mode. A description of each mod is provided below. Let's add a debug interface. We will use SWD for flashing and debugging. FreeRTOS recommends replacing the clock source with a timer, but we won't do that. I am happy with it as is for now. We will set the system clock using a quartz crystal oscillator. We won't change anything here. I've already tested this crystal with these settings and it works great. However, at the low UART speed I typically use, I think you can get by without the crystal. Everything will work just fine. Now let's add the UART settings. We will use it to receive and transmit data from and to the terminal. When receiving symbols, we will trigger and interrupt, placing the data in a queue. We will discuss the queue later. Sending will be in blocking mode, but since we are using the operation system, blocking mode won't be noticeable. You need to set identical settings in PuTTY and CubeMX. We will discuss the PuTTY settings later. Don't forget to enable interrupts. We will use them. In addition to the UART, we need to add a PWM controller. We will use timer to add 2 PWM channels for each motor. We will set the fill width, that is, in this case, the motor rotation speed. Don't forget to specify the frequency. I am using 10 kHz. This frequency doesn't exceed the frequency specified by the TB6612 manufacturer. Setting it above 15 kHz is not recommended, as it will lead to excessive losses. Let's set the system frequency. We are using an 8 MHz quartz crystal, but not a clock crystal. Let's set it to 72 MHz. Let's move on to the OS settings. Tick rate is the number of scheduler calls per second. We will change the number of priorities. We will use semaphores later. We will use memory scheme 4. The creators of this operation system recommend using memory scheme 4. This model allows for combining 3 memory blocks into a single block. For mission critical project, they recommend using memory scheme 1 without dynamic memory allocation. Finally, we will allocate the heap needed for our task and an 8 KB all queue. We need to enable tracing. We will also enable task get stack hide watermark, task get handle. We will retrieve task data by its name. Let's add several tasks, one for the terminal and one for motor control. We will allocate 256 words to each. In our system, a word is 4 bytes or 32 bits. And let's add another task to control the first and second motors. Let's call the task motor 1, 2. Now let's create a queue. This queue will be used to transfer character data received via UART from PuTTY to the STM32 terminal control task. Let's enter a queue name. We will use characters which are single byte, so let's specify that. The entire queue is created and we will allocate elements dynamically. 30 characters will be sufficient. These are all the necessary settings for demonstrating the console. Let's generate the code. Well, they recommend enabling use new lib retrant, so we will do that and generate the code. Now let's include the necessary libraries. We will use a terminal software Anka. I'll leave the link in the description. I combined the console.c file in one folder with the rest. Let's include in the project. We also need to use several functions that will be used for input and output. Anka doesn't know anything about the architecture we are using, so we need to specify which functions are used for input and output. The necessary additional input-output functions are contained here in UART terminal, and we will add them to the project. Let's connect these libraries to the environment. Don't forget to update everything. I forgot that this timer also needs to be made external. Let's set up the compiler and debug. Let's try compiling. An error. The error is because the libraries used the operating system and it needs to be connected. Compile everything. 2 warnings remaining. I don't understand what the warnings is, but whoever understands, write to me. Everything works fine despite these warnings. Now we need to configure the terminal. It's configured in the console config file. This specifies the maximum number of commands. The length of each command includes all characters entered. This is the prompt. I don't know what this is. This is help. When creating a command, you can specify a string that will be displayed in the help for that command. This allows you to delete entered characters. Auto-completion and history are disabled. Let's look at the functions that will be used for input and output. Before launching the terminal, it needs to be initialized, which we'll do in my console setup. Let's add this function to the terminal task. It will be called once at startup. What will this command do? The start UARTRX function begins receiving characters via UART using interrupts. By passing null as the parameter, we initiate character reception via an interrupt. When a character is received, an interrupt occurs. The program will jump to this function and queue the received character in the UARTRX queue handle queue. When control is transferred to the terminal task, it will begin receiving data from this queue using USART1 receive. Let's return to the initialization function. We configure the receiver with start UARTRX. This line defines the function that will output data from the terminal. In the console write function, we receive a string and output it in blocking mode to the UART. However, nothing will be blocked since we are using the operation system. After defining the input and output, we need to register the commands. Currently 2 commands are registered. The comments indicate that the tasks are defined in console func. Let's go to that file, and here with these defines we defined the command itself and the help strings. Next, we need to write a handler for this command. Let's look at the algorithm for the data retrieval command. This displays the unused allocated RAM available to the OS. This displays the elapsed time in seconds. Next, we use the functions we included in CubeMX in the previous step. Here are the two functions, getHandle and getStackWatermark. Then we display the task name, status, priority, and finally the free memory allocated to the task that wasn't used. That's basically why I started this in the first place. We will also add a new task for engine control here, and then we will see how it all works. Let's write a console handle task. I've already written it, I just need to copy it. Let's add these two functions. How does it work? The usart1 receive function reads byte from the queue until it encounters a line terminator. When it finds one, it passes the string to console process. The line terminator is passed to the usart1 receive function. Currently, it's 13 in hexadecimal notation. Console process accepts a command and launches its processing procedure. I'll show you how to add a command and its handle later. I set the start console task to the lowest priority because it outputs to the terminal in blocking mode, which would block all lower priority tasks. Before adding the command, let's implement the engine control task. It will use a global variable that we will modify in the terminal. I've included the engine control library. We will use the engine control function to control two engines simultaneously. These functions ensure smooth motor acceleration. I can't apply a load suddenly. The microcontroller reboots. This may be due to insufficient capacitance at the motor control chip input. I added a global variable that we will be changing in the terminal. I defined it as an external variable in main hash. In the task, structures are formed. They are necessary for determining the microcontroller terminals to which the motor is connected. As you can see, the pins to which our motor's microcircuits is connected are specified here. Each motor has its own structure. Now let's look at the command. M12 is the command name that we will enter in the console. This is the prompt used by the help command to display task information. This defines the argument the engine control command accepts. It also has its own prompted help. We will pass the rotation direction and duty cycle as arguments. The handler must be created correctly. It's important to include the command itself at the beginning of the name, and this name must also be added to the handler's arguments. In the handler, we check the range of values. Now we need to register the command. This is done here. After that, you can begin testing. I'll show you the PuTTY settings. First, let's look at which COM port the USB to detail converter is connected to. You can do this in Device Manager. Below are the settings similar to those entered on the STM32 site. I enabled this so I could erase characters in the terminal. This is the option that needs to be enabled. And don't forget to fill in the checkbox here. Now we can launch the terminal. I'm flashing the microcontroller with the firmware I wrote earlier. Now we are received the input prompt. Let's test the commands. We will display information about the console task. Let's look at the free memory of the motor 1-2 task. We can see that 205 words of free memory allocated to this task are unused. This means that this is the number of words we can free up. I'll show you how to connect to the Cheburlyator debug board. All the pins are labeled here. For the UART connection, we will connect this USB to TTL converter RX to TX, TX to RX cross-connected. I soldered the connectors to the debug board for convenience. I use the ST-Link V2 programmer and debugger. It's a good and inexpensive device. The programmer and debugger use ZH1.5 connectors. We will supply power to this connector. I'll be supplying 8 volts. The circuit is generally designed to be powered by 2 lithium-ion batteries, but for testing I'll connect a power supply. Everything will work stably from 6 to 12 volts. This is the connector for connecting the motors. I'll be connecting these motors, although I use more powerful ones. They have starting current up to the maximum supported by the TB6612 motor controllers. I've connected the entire system. Now we will control the motors from the terminal. Let's run the engine at 10 in one direction. Let's run it at 127 in the same direction. Now let's stop it. Notice they don't stop abruptly, but slowly as expected. Now let's run it in the opposite direction. Now we've completed everything we planned.
That's it. We've implemented the terminal, learned how to connect it to this task, and used it for practical purposes. For now, everyone subscribe to the channel. There will likely be some interesting video. Bye everyone.